Hey everybody. All right. We're all we're all good here. So I believe where we left off, we had finished with the simple Brayton cycle, and so we're going to start talking about regeneration. So how we can increase the thermal efficiency of a Brayton, just a simple Brayton cycle. And so the idea behind regeneration is if you look at that thermal efficiency equation, right? If you want to increase that thermal efficiency, you can either increase the numerator or you could decrease the denominator. And so our first option is going to be to try to decrease that denominator, decrease the amount of heat that we have to put into it, because that translates to less heat. Well, that's less fuel that we're using to for the combustion reaction in order to raise our temperature of that working fluid after it gets out of the combustion chamber. So we're using less fuel to accomplish that. So with a simple Brayton cycle, you've got four process. Well, let's see. Yeah, you've got four processes. It's okay. Keep in mind, don't worry about the numbering too much here. We've got 1, 2, and then you've got 4 or 5. Just take it at face value that we've got 4 states here that we're looking at. So you've got an isentropic compression from 1 to 2, and then our kind of strangely numbering thing from 2 to 4 on our diagram here. You've got a constant pressure heat addition, then you've got an isentropic expansion, and then you've got a constant pressure heat rejection. Those are the 4 processes for a simple Brayton cycle. But with regeneration, what we do is we add another heat exchanger here. So you can see why we had the numbering the way that we did. And now we can kind of compare what that TS diagram looks like for a simple versus a Brayton cycle with regeneration. So the whole point of that regenerator is to take energy that would have been lost, thermal energy that would have been lost in that exhaust process, right? So if I look up here, after that isentropic expansion process, well, that's where you'd have your heat loss, right? You model it as a constant pressure heat rejection process, but that's your exhaust process. And there's still a lot of energy that could have been extracted there. And so with the Brayton cycle with regeneration, what we've done is we've sort of redirected some of that thermal energy back into the cycle. You're still going to have heat loss because that's one of the requirements of the second law, is that you do have to have some heat loss. That's the Kelvin-Planck statement. If you might remember that from Thermo 1. But this just means that you have less of that heat loss. And the other thing that happens is, if I look, okay, for 1 to 2, so 1 to 2, let's follow it along. There we go. So from 1 to 2, we've got that isentropic compression, so the entropy stays the same. And then from 2 all the way to 3, you've got this constant pressure process, right? You know how many fluid friction causing a pressure drop. So from 2 to 3, your heat is going up because, once again, we're capturing some of that wasted energy and we're redirecting it back into the stream. And so the temperature goes up, but it goes up along a line of constant pressure, which, if you recall, those are kind of curved up on a TS diagram. And then from 3 to 4, well, it's still along a line of constant pressure. Sorry, I probably should have put that. Yeah, 2 to 3, then 3 to 4, but all along that same line of constant pressure. So your your temperature is going up the whole time. So from 3 to 4, or 2 to 3, it's because of that Q regen. From 3 to 4, it's because the constant pressure heat addition process, that's where you actually have your combustion reaction. Then from 4 to 5, you have that isentropic expansion process. So your temperature goes down, but it's isentropic, so the entropy doesn't change. And then from 5 to 6, you've got a constant pressure process. It still takes place along a line of constant pressure. But the temperature's going down because that's where you're extracting some of that thermal energy. And then, of course, from 6 all the way back to 1, that's another heat rejection process. Temperature goes down again, but once again, it's still along that line of constant pressure. Okay, so the reason that you have to add less of this Q in is because we have already increased the temperature from the outlet of that compression process. You've increased the temperature because of the regeneration. And so now you don't have to add as much heat to get from this temperature to this temperature. You're only adding enough heat to get from this temperature all the way up to that temperature. Okay, so if you haven't watched the video, I would encourage you, please do make sure that you know that you understand what's going on and why. For our regenerator, we have what's called generator effectiveness. Okay, effectiveness. I don't know that I can fit the NESS there. I probably can. Okay, fine. Effectiveness. Sort of looks like it. So it is defined as this Q regen over Q regen max. So the Q regen, if I draw my control volume, I draw it just around this guy. So I'm just looking at this little loop. So if I apply my first law, remember my first law, it's dE dt, it's all the stuff it's an open system. If it's just that squiggle, I've got mass flowing in and mass flowing out. And so my first law, it kind of looks like this, dE dt dot in minus q dot out, all that stuff. Remember that guy? So it's all in terms of h's. If I say it's steady state, ignore changes in kinetic and potential energy, then it's all going to be in terms, that little Q regen is going to be in terms of delta H's. So it's going to be H3 minus H2. Now ideally, the regen max is going to be the Q regen that you would obtain if by the time that you're working fluid, by the time your air flowed from state 2 to state 3, it would have heated up to the same temperature as this T5. And so if that were the case, then the enthalpy would be the same, right? Because you've got air, it's an ideal gas. For any ideal gas, your enthalpy is a function of temperature only. So for a gas, if your temperature is 300 Kelvin, it's the same. It doesn't matter, what the pressure is. It's your enthalpy is the enthalpy at 300 Kelvin. It's only a function of temperature. So if by the time your working fluid got from state 2 to state 3, it had heated all the way up to the same temperature as T5, then those enthalpies would be the same. Okay. So that's defined by drawing your control volume around that bottom squiggly. I could also draw it around the top squiggly. So if I did that, okay, well my regen would be going out of that blue squiggly, so it would be a delta H between 5 and 6. So it's going to be, let's see, so it's going to be H5 minus H6 over the regen max. So that would be if by the time your working fluid flowed from state 5 to state 6, it would have cooled all the way down the same temperature as state 2. And so in that case, your H6 would be delta H2. Shoot. 5 minus H2. Wait a minute. Yes. Yeah. So you're getting that by applying your first law here to each of those little squigglies to get the delta H. So, and it, you know, it depends on whether it's an inlet or outlet, because you'll have, you know, Q dot in minus Q dot out minus W dot in minus W dot out. And then you'll have some of the M dot H's coming in minus the sum of the M dot H's going out. Right? So when you've got the blue line, that Q regen, it's a Q out. When you're looking at the yellow line, it's a Q in. So you might have in minus out versus out minus in. Another way to kind of figure out whether it's like, say, H3 minus H2 or H2 minus H3, this is all subscript analysis. So that Q has to be a positive number. So you can reason out, well, this guy right here, I know H3 is bigger than H2 because between 2 and 3, I'm adding energy to it. So the temperature is going up. And so my H3 has to be bigger than H2. All right. So that's my definition for Q for the regenerator effectiveness, which I just did. Ah, it's down there. Oh well, so hard I tried. Well, yeah. We've already gone over it, so but it's there if you'd like. So here's if we're defining, yeah, so this is like defining it from that little squiggly. This is defining it from this little squiggly. There you go. All right, so let's work a problem and see what we can do. So problem 5. Problem 5. Air enters the compression of a cold air standard. So cold air standard, which means that our specific heats are going to be assumed to be constant. K is equal to 1.4. Perfect. With regeneration at 290 Kelvin, so it enters the compressor at 290 Kelvin and 100 kilopascals. The pressure ratio is 8. The temperature of the air going into the turbine, I think I put that here, but going into the turbine, T4, it's 1370 Kelvin. And then the isentropic efficiency of the compressor and turbine are each 90%. And then the regenerator effectiveness is 90%. 90% or 70. I think this one. Let's go. That's fine. Let's put it as 90. Let's say this was the typo. Let's do it. It doesn't really matter. Okay. So my solution. So the first thing that I need to do, and I want to find the backwork ratio and the thermal efficiency. I don't even think it told me to find the backwork ratio. Let's say the thermal efficiency and the backwork ratio, because apparently I've got that on there. All right. So get our governing equations first. All right. So our governing equations, I've got our backwork ratio. So backwork ratio. So that's the work of the compressor or compressors if you got multiple over the work of the turbine bends. So for the work of your turbine. So I'm just going to write my first law here. Started to write it up at the top, but got Q dot in minus Q dot out minus, oops, U dot out minus W dot N. And there's kinetic and potential energy terms, but I'm going to ignore those. Actually, I probably should have ignored that because it's steady state, or that's one thing we're assuming. So for the work of the compressor, I know I've got things in terms of Q dots and W dots, but the mass flow rate through the whole thing, it's the same. And so I'm just going to have things, if I divide through by m dot, I'm going to have things in terms of delta H. So for the work of the compressor, for example, that's a work input. And so let's see, if I bring that W dot N over to the other side, so it should be out minus N, the enthalpy going out minus N. So this is going to be H2 minus H1. Remember that little kind of shortcut trick that I taught you, that you could figure out which one goes in front of the other by just reasoning out which one's going to be bigger, right? Clearly, by the time you're compressing it, you're putting work into it to compress it, and so your enthalpy at the end of that compression process is going to be bigger. So H2 is bigger than H1. And then the work for the turbine, that's a W dot out, so it's going to be in minus out. H4 minus H5. You can reason out which one's going to be bigger, because for that expansion process, you're extracting work, so you're going to have less energy associated with the working fluid after you extract work, so your H4 is going to be bigger than your H5. That's of course your, again. All right. And then because we're assuming the specific heats are constant, this is put in terms of Cp delta T. Doesn't really matter what that Cp is, I guess, does it? This is T4 minus T5. All right. So the way that I grade, if you get the governing equation, that's worth a good amount of points, and then I go through and I give you points for the individual properties, the individual temperatures. All right, so back work ratio, and then I also need the thermal efficiency. So I could put it in terms of the work net out and the Q in, or I could put it in terms of just Q in over Q out. And so actually one thing that I will do is I'll just kind of, they didn't draw it on here, but I'll keep in mind that even though, the actual engine, it's open, it's not really a thermodynamic cycle, but we're modeling it as a thermodynamic cycle so that we can, take advantage of some of the really convenient relationships of a thermodynamic cycle. And we're just going to model that exhaust process as a heat rejection process. So I've got a heat rejection process here. This is a Q out. This is our combustion process. This is our Q in. So I'm going to put it in terms of 1 minus Q out over Q in. So for the Q in, it's going to be between 3 and 4. So this is going to be H4 minus H3. And I'm getting that by applying my first law, or kind of taking a shortcut, knowing that it's just going to be in terms of delta H's, and my H4 is going to be the bigger number because I'm adding heat. So energy is going to increase. And then for the Q out, it's going to be between 6 and 1. Enthalpy before that heat rejection process is going to be bigger than after. But really, in reality, you're just applying that first law to figure out whether it's H6 minus H1 or H1 minus H6. And then finally, this is a Cp delta T. So Cp T6 minus T1. And this is Cp T4 minus T3. Perfect. So I've got my governing equations. I'd get a handful of points that way, probably about half the points really, or at least a third of them. And then I need to solve for each of those missing states. That's it. So state 1, I got it. That's given. So I'm at T1, 290. 90. Now I got my state 2. So state 2, well, I've got this, ideally it would be an isentropic process, but I've got an isentropic efficiency of 90%. So for this guy, for state 2s, it's going to be T2s over T1. So it's an isentropic relationship, P2 over P1 to the K minus 1 over K. Now let me plug this in here. So our pressure ratio is 8. Got 543.43. So 543.4 Kelvin. And then of course this guy, got to use my isentropic efficiency. So 90%. Ideally, wouldn't have to put as much work into it. That's a smaller number, so he's going to be on top. This is going to be CP T2S minus T1 over CP T2 minus T1. So the T2, let's see what that guy is. Oh, actually, you know what? I think I used a T1 of 100 and not 290. So do me a favor if you haven't noticed it already. I do apologize. I used 300 for T1 as opposed to 290. So this actually ends up being 525 and 32. Got a pressure ratio of 8. Perfect. Okay. So I think I got a T21, 551 point, let's go 551.5 Kelvin. So as far as, you know, what we're actually plugging in, I'm going to be using this temperature. I'm going to be using this temperature. Okay. State 3. Let's kind of look at where we are. So state 3 is after that regenerator. And at this point, I don't really know that I have enough information to get state 3. So I'm going to kind of skip ahead. And sometimes that's what you got to do. But I do have some information like about the regenerator effectiveness. Maybe we use that. So if I define it, if I define my regenerator effectiveness along that line right there, this becomes, in terms of CP delta T, this will be T3 minus T2. And then CP, the temperature that it would be if by the time your working fluid got from 2 to 3, it had heated up to the same state as 5. And so let's see. That would mean that your T3 would be equal to that regenerator effectiveness times T5 minus T2 plus T2. So I don't know what that is yet, but oops. But I think that'll be the relationship that we're going to use. All right. Then state 4 is given to us. So my T4 was 1370. Let's see, state 5. Same thing. We're going to have a 5s, and then we're also going to have a 5. So this is after that. This is for that isentropic expansion process. So got a T5s over T4 equals 5 over P4 to the K minus 1 over K. And one thing that we'll notice here as far as, the pressure ratio, that pressure ratio that they give you P2 over P1, but because there's no pressure drops, so P2, 3, P4 are all equal to one another, and then P5, 6, P1 are all equal to one another, right? You don't have any pressure drops across the piping of those heat exchangers. And so this guy right here is just 1 over 8. Okay. So my T5s, let's see what he ends up being. So this is going to be 1370 times so it's 756.3. Of course, we don't need 5s, we need 5. So isentropic efficiency of that turbine, it's the ratio of the two works. Ideally, get a lot of work out of it. And so this is going to be CP times T4 minus T5. CP 4 minus T5s. Right. So our T5. So let's see. So that's going to be 1370 minus better. That makes sense. This is 817.7 Kelvin. And then the very last thing I need to do is get state 5 or state 6. So, oh, and I think actually now I have enough information to get to state 3, don't I? So this would be 0.7 times T5 minus T2 plus T2. So 737, let's see if this makes sense. What did I say we were going to use? Did I say we were going to use 0.9? 0.9, I'm sorry. There we go. So if that's the case, 791.1 Kelvin. So let's see if that kind of makes sense. So from 2 to 3, our temperature increases from 551.5 to 791.1. And then from 3 to 4, it increases again to 1370. So the temperature kind of goes in the way that you would think it would go. And then for state 6, there's a couple of ways of going about it. You could use that regenerator effectiveness equation, except instead of defining instead of defining your control volume around this yellow squiggly, define it around this guy and use the regenerative or effectiveness equation in terms of 5 and 6, H5, H6, or T5, T6, and T2. Or could maybe you draw your control volume around the entire thing and you apply your first law there. So if you applied your first law there, you wouldn't have any heat transfer. Yes, you have some Q regen here, but there's no heat transfer across your dotted line there. And so if you don't have any of that, all you're going to have left is the sum of the m dot h's going in and out. So, you know, you could put those in terms of CP delta T's. So I'm going to say m dot times the stuff going in. Sum of the stuff going in equals the sum of the stuff going out. So going in, you've got H2, H5, and going out, you've got H3, 6. You could put those in terms of CP delta T's. Right, so you get a m dot, a CP, 2 plus T5, m dot CP, T3 plus T6, right? So you're, let's see what your T6 is going to be, T2 plus T5. So T2 plus your T5. Plus T3. Okay. Oh, minus T3, sorry. Like, why is that not working? So 578. So for T6, I end up getting 578.1 Kelvin. And the way that I got that, I'm gonna put it down here so it's like kind of cleaner. But the way that I got that is I applied my first law up here, right? And I solve for my T6. Okay. And so for this one, it really is just kind of plug and chug. So I'm going to go ahead and do that. So T2. All right, so I've got 47.3% for that backwork ratio. And then other for the thermal efficiency, let's see. 3. At 50.2%. So let me know if you get something different. Trying to type stuff in at the same time of got a lot of various hardware stuff around. So I guess the takeaway message here is just to make sure that, you're applying isentropic relationships when you're talking about an isentropic process, and not where you're not. So like you couldn't apply an isentropic relationship between states 2 and 3, right? Because that's not an isentropic process. The other takeaway message is if you look at your equation for the thermal efficiency, you have 1 minus Q out over Q in, and what's missing from there, or what's, yeah, I have a Q in, it's not missing. You have a Q in right here, but because it's not going into or out of the cycle, it's not included in that thermal efficiency equation. So the Q in and Q out, it's only for heat transfer into the cycle itself or out of the cycle. That Q regen is just heat moving around within the cycle, but it's not actually leaving or coming into the cycle itself. Okay, you're just moving heat around to where it's more useful and it works for you. Hey, how we doing? Hopefully. All right, so we got about 20 minutes, and let me, is your test. It's like you actually got a good amount of time, so I think we're actually doing pretty well on time as far as what we're covering. So if you do have questions, please slow me down if I need to slow down. All right, but we'll kind of keep on plugging straight, plugging along. Yeah, so your first exam is not until the 28th. So not this Friday, but next Friday. And like I mentioned, when we have tests in person, all you need to bring is something to write with and a cheapo calculator, something that's not programmable. And then be prepared to scan your work in once you turn your hard copy into me. So you'll walk up with your stuff, you'll turn in your testing book and everything, but before you give me the hard copy, you'll just at the front, I'll have a desk out, but at the front you'll scan your work, you'll upload it to Canvas, and then you give me the hard copy. So that way we'll have a hard copy, but we'll also have a digital copy that we could both reference as well as the grader can reference. All right, so how can we increase the thermal efficiency of a rain cycle? So first way was regeneration, which we just talked about, but we've also got reheating. So it's our second option, and then we've also got intercooling. So option 2 and option 3, we're going to sort of talk about concurrently. So we're trying to increase this guy by either increasing this guy or decreasing this guy. So we can increase the work output with reheating. So I know it's a little bit, it's like potato quality here. So what you're doing is, instead of expanding in a single phase, you would divide up that expansion. So 2 or more. To get from, and on here it's labeled as got 3 and 4, and then they've got these intermediate kind of A and B, but you're getting from P3 to P4, but you're doing it in 2 stages as opposed to 1. And we'll work a problem sort of towards the end where we can actually compare, does it actually work, right? If I expanded from, this pressure to this pressure, is it actually going to give me more work than if I did it in a single stage? All right, so see, so in between those expansion stages, we have what's called a reheater, and so you'll warm things back up. You'll add heat. And the idea is, if you remember reversible steady flow work, something in my class we touch on at the very end of the semester. So this is the equation that you might remember seeing, and usually it's really helpful for evaluating pump work, because this guy, this specific volume, it's doesn't change for a liquid, and so that'll come out of the integral and it becomes VDP. Well, this relationship is still valid for a turbine, still valid for a gas. It just means the specific volume doesn't come out. But if I wanted to increase the work output, so basically increase the absolute value of this, well, I'm kind of stuck between these pressures, but this guy is the one that I can change, right? And so with your ideal gas, this is RT over P. If I keep that operating temperature, that average temperature for the expansion stage high, then my specific volume is also going to be high or higher, and so I'm going to maximize that work output for the expansion process. So that's the idea of why that works. And conversely, if I keep the temperature low during the compression process, that's going to require less work, right? Because it's going to decrease this specific volume during the entire compression process between two given pressures. So instead of compressing from P1 to P2 in one single stage, we divide it up and we just remove heat. We cool things down in the middle. So we compress it a little bit, get rid of some of that heat, and then compress it fully to that final desired pressure. So you're compressing in 2 stages or more stages as opposed to just one. Okay. These, like this Q dot out, this Q dot in, come on. Those guys, they do get factored into the overall thermal efficiency equation. Because those are Q dot in into the cycle, and that is a Q dot out of the cycle. Okay. So here we have something that looks kind of ugly, but let's kind of walk through it, and we'll see how far we get. So we have a cold air standard cycle. So right away, we're going to assume that specific heats are constant. I've got a CP given to me, great, with reheating and intercooling. So I think I've got everything that I could possibly want. The only thing that I see is I see one little typo over here. This should be T5. This should be T7. It's clearly a copy paste error. So air passes through into the first compressor at 300 Kelvin. The pressure ratio across the first compressor so it comes in at 300. Pressure ratio across the first compressor is 3. And then the pressure ratio across the second compressor is 3 as well. And then the air enters the second compressor at 300 Kelvin as well. Once the air exits that second compressor, it undergoes a combustion process. So that's the 4 to 5, between 4 and 5. And undergoes a combustion process, and it enters the first turbine at 1200 Kelvin, expanding to a pressure that is 1/3 that of the inlet pressure. So what that means is that kind of the pressure ratio between 5 and 6, it's 1/3. Yeah, I guess I should put that as P5 over. 6 is less than what? Yeah, so that's P6 over P5. Yeah, it would be 1/3. Okay. The air then enters a reheat combustor and enters the second turbine at 1200 Kelvin. So the reheat combustor is between 6 and 7. And then, of course, the T7 is 1200 Kelvin. Expanding to a pressure that is 1/3 that of the inlet pressure. The isentropic efficiency of the compressor and turbine, it's 100%. Then we want to find some stuff. So the back work ratio and then the thermal efficiency. So let's go ahead and get rid of some of this blue text. This guy back. Okay. So with the little bit of time that we have left, I'm just going to draw where my Q ins and my Q outs are, my work ins and my work outs. So I have a work in right here. So this is one work in. This is another work in. This is a work output. It's a work output. From 2 to 3, so keep in mind, like as far as, you got this heat exchanger between 2 and 3, and you might not remember, is it a Q in, Q out? You're trying to work against what's happening during that compression process. So during the compression process, the pressure goes up, the temperature goes up, but you don't want that to happen, so you're going to reject heat. So I'm going to put this as blue. This is a Q out. Right? And then from 4 to 5, this is your combustion process. So this is Q in. Then from 6 to 7, remember you're trying to work against what actually is happening in that expansion process. So in the turbine, the pressure goes down, you're extracting work, the temperature goes down, but you want to work against that, and so you're going to add heat to keep that temperature up. That's a Q in. So 7 to 8, you have another isentropic expansion process, and then from 8 back to 1, that's where you're modeling the exhaust process. And so this is a constant pressure heat rejection process. So that's our Q out. So, if I wanted to let's get my back work ratio. So keep in mind that all of these components, they're drawn a little bit kind of funky here. Let's do. There. They're all connected. So like this compressor is connected to this compressor, which is connected to this turbine, that's connected to that turbine. So it's all physically connected, and so the some of the work output that you get for those expansion processes is being redirected back for the compression process. There we go. There we go. All right, so my back work ratio, let's do my thermal efficiency first. Well, that's fine. Back work ratio. So it's the work for the compression process over the work of the turbine process, the expansion process. So you've got 2 of each, so just make sure that you take that into consideration. So for the compression process, you got a CP T2 minus T1 plus, right, it's going to be in terms of delta H's, but those in terms of CP delta T, T4 minus T3. And then this guy on the bottom, you got the work output, the expansion process. So this is going to be CP T5 minus T4 plus CP T7 minus, T6, T5 minus T6. Fix that because it's between 5 and 6. And then the second expansion process is between 7, 8. So this and this and this and this go away. And then your thermal efficiency You could put it in terms of 1 minus Q out over Q in, or the work net out over Q in. It doesn't matter. In fact, it would be a good idea to calculate it both ways so that you know you get the same answer both ways, and that way you verify that you got all those temperatures correct. But put it as, I gotta Q out over Q in. So you have multiples that you have to keep track of. So with the Q out, you've got between 2 and 3. So CP will be T2 minus T3 plus CP, and then it's between 8 and 1. So T8 minus T1. You're wondering, why is it 8 minus 1, not 1 minus 8? Apply your first law for an open system to that heat exchanger down there at the bottom and figure it out. And then your QNs are going to be between 4 and 5. 5 minus T4 plus CP, and I've got it between 6 and 7. So T7 minus T6. All right. So I've got my governing equations. That would be worth quite a few of the points that I would earn on my test, and then I'd have points for the various temperature values. So yeah, we only have 4 more minutes. I'm gonna go ahead and stop right there, and then we'll wrap up this problem. Let's see what else we've got. I don't think we have much more. 1, 2, 3. Got 3 more problems. Yeah, we can. I'm not going to move any tests around because, there you go. And I typically don't just make up extra problems. If we get through the problems, we get through them early, and then I just sit in my office and during the time we would have had class, if we do get through them, because I can see us at least finishing a day early, but we'll see. And I would just use those as extra office hours if you had time, if you had other questions. So just so you kind of have an idea of what might happen in the next couple of lectures. Okay. You guys have a wonderful day. Yep. Enjoy the rest of your day. Okay. We'll see you on Friday. Thank you.